We are in lesson 55 and we're going to talk about circular permutations. So all we've talked about so far has been linear permutations. And with linear permutations, let's say you have three things and you want to know how many permutations there are. We would say 3 times 2 times 1 would equal 6 permutations. But whenever we have a circle, then that changes. It changes because we don't have an opportunity to switch out the first one every single time. Say, for instance, we have a table, right? Here's a table. And we have a king, a queen, and a prince sitting at the table, right? Well, we can move them all to the right one space. Let me draw another circle here. We can move them all to the right. Let's say the king is now sitting here, and the queen is now sitting here, and the prince is now sitting here. They're in different locations, but if you look, they're still in the same order. And if you did it one more time, where they all moved to another chair again, and that's supposed to be a circle, we'll pretend. Well, then if the king is here and the queen is here and the prince is here, they're still in the order of king, queen, prince, king, queen, prince, king, queen, prince, and back to king. So it's the same. Those first 3 permutations are really the same thing if we are considering circular permutations. So there's really only 2 other ways to swap it out. So let's look at that. So the only way to swap it out is, instead of changing locations, they have to get up and change chairs. They have to change, instead of moving around, which is what we do with a linear equation or linear permutation, we have to swap the spaces. So king would stay in his place and the queen and the prince would swap positions. Okay, so now you see that king, queen, prince, king, prince, queen, back to king. Those are your only possible permutations that are any different. Because if at this point, if you just were to swap the prince and the king, it would still be king, queen, prince, just like here, king, queen, prince. So your only other possible permutation, you only have 2 permutations with 3 items, not 6. So we have to, for these 3 spaces that we would normally have, the first space stands in for the 3. So we don't have 3 in the first space, we have 1. And then we have 2. And then we have this. Then we have our exclamation point for permutations. So with 3 spaces, the first one is always 1 because it's the same thing all the way around. And then we subtract and we go on to the next spaces like we normally would. We subtract 1 from the total and we work our way down. So in the event, let's see that we had, let me clear this. If we had a circular permutation with 5 things, right, this is a circular permutation, and we have 5 things. The first space would be 1. This would be 4, 3, 2, exclamation point. So then this would be 4 times 3 would be 12, times 2 would be 24. This would be 1. So that would be 24, would be that type, would be the permutation there. So let's do that with 6 things. Actually, let's just go ahead and do our first example problem because it is 6 things. So example 55.1. How many ways can 6 different items be arranged in a, all right, so we have 6 items, and that would be a linear how many in a linear permutation, and how many in a circular permutation. All right, so with a linear, we'll call this A and we'll call this B. For A linear permutation, there's our 6 boxes. We would do it just like normal. We would say 6, 5, 4, 3, 2, 1. We would multiply them against each other, and our answer would be 720 permutations. For our circular permutation, we have, let's do our 6 things here. So we would have 1, and then 5, 4, 3, 2, and 1. Because even if we do the exclamation point, it's just 1 after the 2, so it doesn't matter. 1 times 5 times 4, that's 20, times 3 is 60, times 2 is 120. So you can see there are far fewer circular permutations than linear permutations because the spacing has a break. And so that order doesn't loop back on itself and get reconnected. And that affects how that first one works. All right, so let's do 55.2. Let me look at it. 55.2. So when the chips were down, Ed found that there were 5 of them, each a different color. How many ways could Ed place them in a row? How many ways could Ed place them in a circle? Well, if you place them in a row, it'd be a linear permutation, and then that would be beginning with the number of items there were, 5, 4, 3, 2, 1. And when we multiply that together, we get 120. In a circular permutation, we start with 1, and then we have 4, 3, 2, 1 times each other. That'd be 4 times 3 is 12 times 2 is 24. And that is the number of circular permutations that we could have. So just remember that whatever that first number is, you're going to replace it with a number 1. That is the difference between the linear permutation and a circular permutation. That first number just gets replaced with the number 1 or the factor 1. So let's talk about distinguishable permutations. Now, before we move on to distinguishable permutations, notice that we had 5 chips here and each of them were a different color. What if some of those had been the same color? How would we have been able to tell which, like if we had 2 reds, which red was in this position versus the other red being in the other position, and how do we know they're not swapped? So that is what distinguishable permutations is all about. So let's talk about that. So if we ask for a number of permutations of the letters in the word moo, right? So we have moo. 2 of these letters are the same. Now we know that in a linear permutation, which this would have to be, we would have 3 things, 2 things, 1 thing. That would be 6 permutations. So let's try to write that out using these letters. And I'm going to label this as O number 1 and O number 2. So we could have, just like the original, then we could swap these. Then we could do O1, M, O2, and then O2, M, O1. And then we could do O1, O2, M, O2, O1, M. But as far as if these are not labeled, there's really only 1, 2, 3 distinguishable differences. If we erase the subset, the subscripted numbers right there, the only thing that we can see is mu, OMO, and That's it. Unless these are labeled with something to distinguish them, the permutations look alike. So there is a formula for telling us how to do this, how to figure out how many permutations that we can distinguish from another there are. And that is going to be the number of permutations possible divided by the number of alike permutations. So, for instance, with the letters mu, we had 3 items. But we had 2 letters that were the same, and then we just had 1 letter that was the same, right? So that would be 3, actually that'd be 3 times 2 times 1, so that would be 6 divided by 2 times 1 is 2, times 1 would be 2. So we would only have 3 distinguishable permutations. MOO, OMO, and OOM. Those are our only distinguishable permutations given that 2 of the 3 characters were identical. That's all we can tell apart. And that is the number that we have. So this is the formula that you're going to use. And A, B, and C represent identical items. So if you have, and you always start with the highest one first. So if you had a word, let's try, let me erase the page. Let's say we had the word start. We have 1, 2, 3, 4, 5. So 5. And then we have 2. And then we have 1, 2, 3 left. I think that's right. No, I'm sorry. These are 3 different ones. We have 3 that are just ones. So 1 times 1 times 1 would be 1. So technically, if we have individual items that are singles, we drop them off. We leave them out. So 5 would be 120 divided by 2. That would be 60 permutations that are distinguishable from the word start. Let's try another word. Let's do an example problem. So we're going to use 55.3. We have this person named Jojo. He has 10 marbles, or she has 10 marbles. I'm not sure if Jojo is a boy or a girl. It's a boy, sorry. If 3 of them are red and 3 of them are blue and 4 of them are green, how many distinguishable permutations can he form? So we write it out. We have 10 total. We have 3 of one, 3 of another, and 4 of the final. So we can just factor this to figure it out. We don't have to do all of the calculations. So 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. All right. So I'm going to take this 4 4 times 3 times 2 times 1. Cancel those out. Those are gone. So I'm going to take this 3, and I have a 3 and a 2, right? 3, 2, 1. I can take the 1 away. And 6 is 3 times 2. So I can cancel those. That's gone. 3 again is 3 times 2 times 1. The 1 goes away. And I know that in the 9, I have 3 times 3. So there's a 3. And in the 8, I have 2 times 4. So there's a 2. So what I have left is 10 times 3, times 4 times 7 times 5. And that is going to equal 4,200. So that'd be 30 times 4 is 120, times 7 is 840, times 5 is 4,200. So that is how many distinguishable permutations that we could have with 10 marbles, 3 red, 3 blue, and 4 green. Does it make sense the way I factored all those out? If that doesn't make sense, please let me know. I just wanted to not have to do all of that math in my head. It's just faster when you don't have to deal with a division problem later with the denominator. So let's look at 55.4. So 55.4. How many distinguishable permutations can be formed from the letters in the word nonsense? All right, we have 1, 2, 3, 4, 5, 6, 7, 8 total letters. But we have 1, 2, 3 N's. And we have 1, 2 S's. And we have 1, 2 E's. And we have 1 O. And we don't have to worry about the O because it's a single. So it would just be times 1. So we can leave it out. So we're going to factor it. 8, 7, 6, 5, 4, 3, 2, 1. I'm going to take the 3 out first because it is the bigger. So these are gone. Now I'm going to take the 2 and the 2. So that would be 2 times 1 and 2 times 1. So that one's gone. And I know this 4, and I did not do this right. That should be 2 times 1. 4 is 2 times 2. So I can take this 2 and this 2 from the 4. So now all I have left is 8 times 7 times 6 times 5. That's all over 1, because I have 1 and 1. So that's a whole number. So 8 times 7 times 6 times 5 is equal to 1,680. That's how many permutations, distinguishable permutations, that we have in the word nonsense. So this is, kind of fun. Let's do one last one, and then we will be done with lesson 55. How about that? That wasn't so hard. 55.5. So how many distinguishable 7-digit numbers can be formed from the digits? Now we want 7 digits, right? And we have 2, 7, 2, 2, 4, 2, 4. Let me make sure I wrote that down right. 2, 7, 2, 2, 4, 2, 4. Okay. We have 1, 2, 3, 4, 5, 6, 7 digits. So we're going to use all 7 digits. So 7, exclamation point. And then we have, let's see, 1, 2, 3, 4 2s. So 4 alike. That's this one, this one, this one, and this one. And then we have 2 4s that are alike. And we have this 7 that's by itself. So we don't count it because it would just be a factor of 1. So 7, 6, 5, 4, 3, 2, 1. And I'm going to start with a 4 because it's the bigger one. 4, 3, 2, 1. These are gone. These are gone. So now I have 2. Do I have something in here? Yes, I do. The 6 can be 2 times 3. So 2 times 1 would be 2 gone away. So I have 7 times 3 times 5, which equals 105. And that is how many 7-digit permutations I would have with the number that I was given to start with. So I hope you're getting the hang of how that works. Remember that we have the number divided by the most alike, the next most alike, and if we have another most alike permutation, and any singles are dropped. Right? From the denominator. So we don't count those. We just do the ones. These are just the duplicates. So these are just the duplicates. This is the total number. These are the duplicates. And this is the quantity. A, B, and C, those are the quantity of each of the duplicates. So here we had 4 of the 2s, 2 of the 4s, and we only had 1 7, so we dropped him. But we had 7 in all. All right. That's all we have for lesson 55. I will see you in lesson 56.